Morning. So we are now in week 07 lecture B. Okay. Today we are going to continue on chapter 8 on uncertainty modeling. I'm recording this lecture because this chapter is very important for us. I think we should clarify about uncertainty here. So uncertainty here, of course, we do not know 100%, but it does not mean we do not know anything. So far, we only assumed that the uncertainty bound is less than 1. And the 1 is just for scaling, for easy to discuss. And we usually use infinite norm to less than 1, okay? So that's uncertainty after normalization using scaling, filtering, weighting filter, and so on and so forth. So basically we say the uncertainty, we only know it's bound. Otherwise, we don't know anything, okay? So this type of uncertainty actually is called unstructured uncertainty. There's no structure in that uncertainty. We don't assume anything. It's just like black box. We know it's bounded, okay? But inside the box, what's the structure? Is it like diagonal or fully populated? We don't know. We don't assume. We don't know that. What if we can see through the black box, know something that is called structured uncertainty? Okay, structured uncertainty. So for unstructured uncertainty, we only focus on chapter 8, okay? Chapter 8. In chapter 8. It's called unstructured uncertainties. And these unstructured uncertainties, so we live with that through what? Small game theorem, okay? Small game theorem. I have shown you that the small game theorem is a very important theorem that we use all the time to solve this worst case scenario, okay? And we, again, keep talking about robust stability. So it's RS or nominal stability. Robust stability and robust performance. Okay, so it's a robust performance versus a nominal performance. So these are the things we discussed last time, but we left this robust performance. We haven't discussed that yet. Okay, but for the last time, we already had a pretty good idea about what is a robust stability. That means if you check the small game theorem, you will be okay, have a peace of mind. Okay, peace of mind. So when you have this signal here, uncertainty here, and it is less than 1, okay, less than 1. And from signal and system point of view, okay, signal and system point of view. So you can guarantee that the signal, okay, so we should say that the delta is not just the signal, it's uncertainty in the model, okay, in the model. In the model, okay, in the model. So the model means you have some driving signal and you have an output signal. Let's say this is delta t. But the delta t probably is not a very good idea. Well, let's do this. Let's do a disturbance due to this delta. This is a disturbance signal. Make sense? But sometimes you don't have this, so what you do is 1 over S. So it's a Laplace transform, so you get the delta t impulse put as an input, right? So as an input. So, all right. So now I say that you have step in here. Then I got another signal like D. This is like step. Let's do this step. So we'll have signal going through this one. I have this one, right? Because this infinity less than 1, what I can say. So I can say this guy is always, absolute value is always less than 1 for all t. This is really strong and give you the confidence. And the infinite norm is already what? It's already worst case. So no matter what, this is always true. And it is for all t. This is very strong, right? This is very strong. And because this is also 1, right? So this is also 1. So of course you have delta infinite norm. Okay? So that's the beauty. That's the beauty. You don't need to care about transient or steady state. It's for all t. It's for all t. This is very beautiful. Okay, this is very beautiful. We had a discussion on this before. Okay. So for here, that will be our next week's contents. That will be LFT, called linear fractional transformation. Okay, linear fraction. How to systematically address this structure, how we can exploit the structure information in the uncertainties. That there is a systematic mathematical vehicle. So the LFT is like a math vehicle. Vehicle means a tool, okay? To exploit the structure in the model, uncertainty, if they have structure. And with that, we can define systems. SSV stands for structured singular value. Structured singular value. Meaning we are going to not only using sigma bar, this is unstructured information. We also talk about the sigma bar due to the structure set. This is very interesting, okay? So from now on, I hope you understand that what we are going to do. So that will be our chapter 09. This is chapter 10. Okay, chapter 10. So we are going eventually, because otherwise, if I treat everything as unstructured, that the reason we cannot live with this alone is because that could lead to a huge conservatism. Okay? Conservatism. Okay? And if you know the structure and how to make use of the structure, that's the next lecture. So today I'm going to do 3 things. Okay? The first one is to quickly go through what we did about robust stability, homogeneous theorem, quickly go through. Then there's also a table depending on where and how the uncertainty will enter into the system, and how we can do that. In page 145 of the textbook, there is a table. So I think you should be able to derive that table yourself. The second part is I'm going to go through is Astrom's he has made about 38 pages write-up plus 80 pages of slides. I uploaded to our week 7 CAT course directory. Okay, so I'm going to go through with you on this as well. So you see from his view about clarify the model uncertainties and the robust control, how they are connected hand in hand. Okay? And we are, in fact, it's better to learn this one in the end of the course, so you can have a very nice overview when you climb to the top of the mountain. Take a look. But now we are in the middle of the mountain. But also it's a good idea to see what he sees about the robust control and model uncertainty, because we are on this chapter on modeling uncertainty. Okay, so that's then we are going to take a look of Kharotonov's H theorem. Because this was in 1980, in early 1980s, 1970s to 1980s, in the robust control community, people believe that's everything we should know. That's enough to know what is Kharotonov's theorem. And ironically, or humorously, that this is presented as our homework question. Homework question, okay? In chapter 07. We're going to take a look, okay? In the 1980s, maybe in the middle 1980s, even in the early, as far as I know, in 1995, this year I went to Singapore for my PhD, 1985. And I know there's a guy who's so proud that he knows everything about Kharotonov's work, and all different generalizations. And they believe the robust control is all about Kharotonov. And today, we zoom out and take a look the subject area. This only is a homework question. So with that, I hope to remind everybody that the framework paradigm is more important than individual technique. Okay? Framework. So instead of we study each individual case, so I hope when you do research, you put more focus on framework first, then zoom in to solve individual questions, instead of you just solve one question, okay? Or we know people use an analogy saying that versus a tree versus a forest, right? Okay, tree versus forest. So we're using this one as an example. So with that, I'm going to run slides. Any questions? Okay, so I think it's an interesting lecture today, so we record it, so you can review, okay? So what I'm going to do now is to run through this chapter 8 slides. No, it's here. Display, screen down. So let's go to our slides. So we started by talking about model uncertainties. I said a lot of interesting things about uncertainties. Okay, it's a philosophy. Okay, it's a philosophy. We will be no longer working with a single model GOS. We are working a family of them, okay? Infinitely many of a model set, okay? It's a model set. So the modal uncertainty, then small gain theorem. We talk about additive uncertainty, multiplicative uncertainty, and this one, coprime factorization uncertainty. As well, I give you one more way to specify the format of your uncertainty. And now, today we are going to start from here, robust performance. But let's do very quickly. And we talked about NSRS, MP, RP, and we talk about the pi is my model set. There are multiple ways to define the model set. Okay, define the model set. Okay, define the model set. There are methods that can make this set very tight, or you make the set very big. Okay, so unnecessarily big, you will make your control design conservative. Okay, so we'll see two examples, and it's explained in the textbook better. And there's a dedicated command that can help you to do this type of plot, so you understand how conservative it is. So even for the most commonly used model, this one has a name for FOPDT, fractional order plus time delay. Okay, PDT. Okay. So then all three parameters can be in the interval. Then how you can do a nominal model. Of course, here they all do this in the middle. I don't think this is the best way to do. We'll talk about this in the future. And then we have multiple ways to draw this type of scanning and this uncertainty realizations. And then you can do this in terms of additive versus multiplicative formats. Okay. Of course, these are all Sizer case, but in MIMO case, it's more complicated. Okay. So far we are not talking. About the uncertainty with any structure. Okay, with any structure, we don't even need to think this is uncertainty, but it's just a system with this connection. Okay, with this connection. Of course, I told you, we better to realize that we pull out all the uncertainties out, and this is my nominal model. We have this separation, then we decide whether this is robustly stable, then we rely on this small gain theorem. Of course, we are talking about this delta is also RH. Okay, this is quite important. I'm going to show you. This is a quite important assumption. People ignore it. RH infinity. RH infinity. Is a constant an RH infinity? The constant. Think about it. We'll go through. We'll have an example I'm going to show you. So usually, you probably should have frequency dependent ones that is stable, proper, but may not be strictly proper, right? RH infinity. So in that sense, proper, not strictly proper, then constant is RH infinity. The constant, right? So this one says, if we make this less than 1 over gamma, if infinite norm of the m, or both of them are MIMO, okay, less than gamma. So in other words, this norm and this norm multiplied together will be less than equals to 1, less than or equals to 1. So you will be okay. Okay. The whole thing will be internally stable, well posed, okay, well posed. In a MIMO case, whenever you do this type of MIMO connection, you need to worry about internal stability. So remember, if this guy is internally stable, this guy is internally stable, when you do this connection, it may not be internally stable. hard to say. It will change. That's why the control is hard, because the control, you can do good thing, you can also do bad thing, okay? So the closed loop could be stabilized or destabilized. So that's the key point. You need to satisfy some stability condition. And this one is very universal small gain theorem. Meaning, if you satisfy that, everything will be okay. There's a 3-page long proof on our textbook going through the decomposition using maximum singular value decomposition like this, definite dependent, and do that kind of argument. I'm not going to go through this one with you. I don't need you to prove that. But you just know that if the loop gain is less than 1, there's no way to be unstable, okay? Because the signal will not be amplified, okay? At all, okay? For all t, all the time, all the frequencies, okay? So that's very strong, okay, very strong. Do you see what I'm saying? This is for all frequencies, and it is also for all t. Okay, all t. As I mentioned, okay. So it's very strong. Okay, very strong. So then we have different formats of this additive uncertainty connected to this add on top of the nominal plant. This is my controller. So then by normalization of the delta, I know W1, W2. This is, we know it. But this one is normalized less than 1. Then this is P, this is K. So then by this setting, I can check what is the nominal stability. What is the robust stability condition? So this less than 1. So the robust stability of this control is equivalent to checking if this guy's infinite norm is less than 1. Then use small gain theorem and say you can draw that conclusion. So robust stability checking, RS, is solved. So it's giving plant, giving the uncertainty, and giving the control. Then I tell whether the control K is robustly stabilizing the whole system, infinite settings. The answer is yes, RS if this infinite norm less than 1. This derivation is not hard to do. It's very easy. Okay. The hint is you assume that everything here is scalar. Okay. Assume everything here is scalar. Then you use the signal flow you derive. Then you have something like this. But if it may happen that you switched them a little bit, but then after the vector form, you really need to follow left multiplication and the right multiplication separately and carefully. Then get this. You cannot change sequence at all. Okay. That's for additive. For multiplicative is this, then you have covariant factorization like that, then you are going to have other tests. You have a long table that is on page 145. Page 145. So I'm going to pull out the 145. So just one page long. No, 145 is here. Is table 8.1. So basically, you have this is my mouse. So you have So you have a pi. The pi here is your. The pi here is your set of all plants with nominal plant as P, others are uncertainties. And while the uncertainties is described in a multiplicative way, this is an additive way. So you have a weighting filters W1, W2. So then we have this is robust stability test. So this is a test criteria. Okay, test criteria. So these are the test criteria. Okay. So with different forms, you can have different criteria, and these can be derived. Okay, they can be derived from the signal flow. Just be careful about left multiplication and right multiplication, or about signal flow direction. Okay, so that is what we have here. So it's called RS tests, the table for different formats of uncertainties. In your homework questions, you have practice on some of these. So again, I want to remind you, everything we talk about here, uncertainty is called unstructured uncertainty. So we don't talk about what's inside the delta. It's unstructured uncertainty. Okay? And the delta, it could be fully populated. Okay? Fully populated. Or the delta is a matrix, transfer function matrix. It could be diagonal or block diagonal. Okay? There must be a difference. That's the topic for the next chapter on RFT. How to systematically pull out those uncertainties and forming the different structures. And exploit the structure. Redefine singular value as structured singular value, or SSV. We're going to talk SSV in next chapter. Okay. So today we are going to talk about robust performance, and this part is actually pretty simple in a sense. So you already have a system. You already have a system under control. So this is a set of your plant. Okay, set of your plant. And so I have uncertainty signal in here. My from D to E. So TED is from D to E, okay? You should write D to E from right to left. So don't write E, T, D, E. That's not making good sense. Because when you have the T, E, D times D, then you start to flow from here, okay? You get the E. So if you write T, D, E, not T, E, D, that means you don't really capture the MIMO nature of the thing. Don't swap that. Okay, don't want TED, okay, TED. Don't do TDE, okay? So then you can see that the D will get a weighting filter as a weighting, so we don't use Y directly, we use a weighting filter transfer function matrix. This is a given, okay? Depending on your preference and your design spec. I generate an output signal E to make that as my performance requirement. So T stands for what? Complementary sensitivity function. We know T has another name. What's that? It's called closed loop transfer function. In and out from, this is in, this is out. Then we call this is a closed loop transfer function. So you could say R, you can do T, E, R, okay? You can do that as well, okay? So that's called closed loop transfer function. And again, this is an LTI system. So when I consider my E due to D, I consider R to be 0, okay? To be 0. But on the other hand, so you can see from here, the TED is the closed loop transfer function from D to E. We write this complementary sensitivity transfer function matrix T. It's a subscription of E and D. That's the signal going from right. So because E equals TED times D, okay? And this time D is a vector. We should write vector on the right side. Okay, on the right side. So this is a transfer function matrix, and the size of the row depending on vector E and vector D, the size. Okay, that could be not square. Okay, could not square. But anyway, you can see because this one goes to Y, direct to E, and the Y will go through this. So there is something called, this is from D to Y is like 1, okay? You pull out this one in the bottom, so it's 1 over 1, the loop is 1 plus PKE. So you think about this size of bits, okay, size of bits. So this is called output sensitivity function, then becomes this. Okay. So what do we mean? Performance objective is to have a closed loop transfer function having its worst case infinite norm, so that for all the D, 2 norm less than 1 is induced norm, okay? The worst case of output is 2 norm is less than 1, okay? It's less than 1. So that's our objective, okay? Objective. Okay. Objective. Okay. So performance objective is not to amplify the guy, okay? Not to amplify the guy. Is to attenuate it in the worst case scenario for all frequency, for all T.
So we are talking about performance. Isn't this still like a stability type of?
No, you are already stable. So we usually ask the user to ask the system designer to say, oh, make this one less than 1. You can say less than gamma, okay? We can tune the K to satisfy this one. You can, doesn't matter if it is not 1, okay? But usually when you say 1, meaning you are not having any amplification of the disturbance, which is usually true. 1 always suppress my disturbance. Okay? But it could amplify in certain cases. Okay, certain cases. So this is usually true, but if you say TER, then the TER that could be less than a gamma. Okay? Because say for example, you may have an overshoot. Okay, so it's greater than 1, so it's possible. Okay? So then we are going to talk. So this is my uncertainty set. I have a W2 in here. Remember this is WE. So these are the filters you introduced by the designer. And make sure that delta is RH infinity, delta infinity, H infinity as well. So this is a standard uncertainty set. We use this one, call it pi sometimes, or use P delta. And then we design the K, stabilize the P. How we can design a K, it will be after 2 more chapters, okay? But suppose we design that, we say, oh, this is not enough with stabilization. You still need to guarantee this is also true, okay? This is also true. Now how you do that, okay? You want to ensure this is true, then basically you have a sensitivity function of this one, basically it's this one. Okay, WES, so sigma bar, and also sigma bar W2 and TO is depending on the output. Okay, so these are kind of performance requirement for the response of the E due to E due to R. So this is called robust performance is guaranteed if we can design the K such that S0 T0 and its waiting filter, the maximum single value less than 1, and everything will be satisfied. Okay, that's not very hard to justify. So that kind of robust performance.
What is W2 here? Oh, okay.
Yeah, W2
Yeah,
is
that's nice.
is in a
Yeah.
uncertainty filter. But the question is, you tried a K, but this didn't satisfy. Then you need to iterate to find another K, right? That's already synthesis process. We are not there yet. Okay. But just to tell you that if you say you want this performance, you design a K, then let's check whether we have satisfied the performance in a robust way. We say, oh, given this uncertainty set, then we check these two maximum singular values, whether this is less than 1. If yes, this is true. Okay? So that's kind of performance checking. So be careful. Performance checking, you need to define performance first. Okay? When you do define a performance, you need to introduce the WE. And in reality, WE could be what? Could be I, right? Because E is 1. Can be like that. So that's not a big deal. Let's move on. So that's robust performance. So what if I say I have a multiplicative uncertainty like this, okay, like this, and we design K, make it stabilized. How can I make sure this is stabilizing? We do small gain theorem, right? So we can do that. So the robust stability is to check the W times Ti. You pull out the delta, then you have the rest is the Ti. So nominal performance is W as 0. So you have W here. Again, this is E. This is the signal. This is the signal used for performance measure. Performance measure. Okay. So W could be I. Then so this is a TED. I'm sorry. TED is complementary sensitivity function from D to E. So you will see that it amounts to W left multiply SO. This is the same as we did it for the last time. Okay? This one is the same here. This is a TO. Okay? The TED. Is it the same as what about? Okay. Okay. So interestingly, here we are talking about something called condition number. Okay? Do you have an idea of giving a matrix? What is the matrix condition number? You probably forgot. So you have a matrix A of constants. Okay? What is the condition? Condition number.
The maximum
Singular value divided by minimum singular value. So if the minimum singular value is 0, then this matrix is singular. In other words, a singular value, matrix is a singular, then its condition number is infinite. In other words, I also can check the sigma bar divided by sigma under bar, this condition number. The bigger, that means the matrix is closer to non-singular. Make sense? So it's also true for systems. Your singular value, maximum and minimum, they have very big distance. Then your condition is not considered as good. Okay? Not considered as good. So, but in our case here, we introduced a kappa here, which is condition number. Okay? Condition number. So this condition number introduced can be useful for us to solve some of the interesting questions. There was an example to see this law of condition number, to use this one to solve. Okay? So these are both true. Okay? If they are both true, then the performance is guaranteed. Okay, robust performance is guaranteed. Kappa. This one is conditional. So the P is the nominal model. Remember, is 100% none. Even the P, you can get the kappa. Okay, you can solve it. There's a way to do that. Maximum singular value, minimum singular value. So there are some examples to do this. So this example is shown in our textbook here. Page 153, there's an example. You have who's exactly the same here. Okay. Okay. So very interesting. Okay. So did I use this W? I call this W as weighting filter, right? I think sometimes I use the name called conditioner or conditioner. You wash your hair, you have hair washer, shampoo, and then you have a conditioner, right? Do you understand what is the meaning of conditioner? And this conditioner is something linked to condition number here, okay? Okay. So basically, we can purposely introduce something to condition our plan, nominal plan. We can do that. And that's next what we will talk about. So you can see that we have two ways. We have two ways to describe the uncertainty set. So this is multiplicative. Okay. So you pull out this one P, or you can on the right side. This is left side, right? Left side, right side. And so both are okay. Both are okay. So one is written as P times this, okay? WT. Okay. This is quite true that the signal will go from here, multiply this guy, then you multiply this guy. So be careful about the signal flow. So from right to left. Okay. This is from left to right. Okay. So there's another one we can write. This. So then we keep the delta the same, but the WT tilt is different. So you can see this is left, okay, multiplication. And then again, this delta is less than 1. So, okay. And so if you multiply the P times this IW, this one, okay, and this is the set I have. And then they also do something, P, do this, WT, WP, so then you can pull out this P in here, then as if you put P in here, okay. Remember, so we have a similar format in here, okay. Okay. And then we are going to do is have an example here. We have A, B, C, D. What is the system? How many input, how many output? 2 in, 2 out. How many number of, how many states? 3, right? 3. So this is 3, this 2 is 3 by 2. This is a C matrix, 2 by 3. D is 0, so it's a strictly proper. Okay, strictly proper. So when you do this one, you are going to have a nominal model and transfer function matrix is like this. A of S is written in something like a polynomial. So we can write this one into this is my A based on that. A. So based on this system, we can try to check the system P has a singular value. Pj omega for all. This is the omega for different omega. You scan this omega, then you have a complex matrix. Then you just do a maximum singular value and minimum singular value. So this is called kappa. So the reason we show this one to you is you have two orders of magnitude difference. Okay? The minimum is here, the maximum is here. 2, 3 orders of magnitude difference. That probably is not a very good sign. You need to take care of such a wide range of conditions. That condition number probably will tell you how hard the system to control. So if you want to do research based on this information, that would be interesting. I didn't read a lot of papers. I don't see a lot of papers talking about using K omega as a design input information. But this is a good view about your system is more difficult to control or less difficult. Okay. So with that, I think we did this performance issue. And again, performance issue is performance issue is linked to the robust stability issue. Okay, it's very similar. If you define the robustness, performance objective clearly. Okay, so again, everything we talked about on the chapter 8 is uncertainty. We should put another thing in front of it. It's called unstructured uncertainty. We only know it's bound. We know nothing about it otherwise. But on the other hand, there's another thing we ignored. I want to highlight. We keep forgetting this. That is, sometimes people forget this. This one. This one. Meaning, when we say small gain theorem, we basically need to make sure the two parties are both RH infinite. Okay. But you may say, wait a minute, my system is open loop unstable. I cannot do much about it. So then you should not use that small gain theorem here because we are violating this. Okay? You cannot do that. What you should do then, just stabilize it first. Okay? Stabilize. Using simple stabilizing controller to stabilize first. Then you improve the control performance or stability margins using other methods. So for open loop unstable system, they no longer satisfy this RH infinity. Okay. Again, let me repeat what is RH infinity. Last time I may say it wrong. It's not strictly. So it's just said proper stable transfer function matrices. A space for that. Okay, so I have a collection of Astrom's stuff, very nice. But he wrote 38 pages. See, I know how many pages. 38 pages of model uncertainty and robust control. And we are in chapter 8. Please go through this chapter quickly. And you will see that we actually covered many concepts in it. You see, oh, Dr. Chen mentioned this part. So to do that, reading this one is hard. Probably takes you a long time. Okay. So, but I'm going to show you his slides. You will love it. So he started by saying that the reason we do feedback is because of what? Uncertainty. If there's no uncertainty, we don't have to do feedback control. Just do a sequential, make sense? If everything is certain, we don't have to do feedback control. So the reason we do feedback control is because of uncertainty. So I like this. You can see this is 84 slides. We don't have time with this really good slide. I'm going to go quickly with you. And this first few slides, I love it very much. We haven't, I think we talked about limitations. Okay, I'm not going to do this. This is a topic several weeks away, actually, infinity loop shaping. I'll talk to you later. And this one is also far away. But this one, basically, we covered all of them. So gain phase margin, PM, basically indexes for robustness, in fact. So the reason we do feedback control is because of the uncertainty handling, okay? If you have no uncertainties, then there's no need to do feedback control. So everybody knows this. But I love these two sentences very much. So you have two attitudes about uncertainties. So one attitude is, so we don't do anything, we have uncertainties, we live with it, okay? So that's called a robust control, okay? Make yourself robust. You live with the uncertainty. But oh, I don't like the uncertainty, how I can reduce it? Or, then you do adaptive control. I like that. And yet you know that so I said any type of control you should question, is it optimal, is it robust? But we haven't talked about how actively live with, not just passively live with uncertainty. What if I also want to learn those uncertainties so I understand the uncertainty better, so I can cope with it better, and so that equivalent uncertainty is minimized? That's called adaptation, adaptive control. Okay, adaptive. Okay, adaptive control. So in fact, we don't have a dedicated course here yet on adaptive control. But if you design adaptive control, you still need to, so you adapt to some uncertainty. So you still need to make the adaptive control robust. So there's some robust adaptive control. You can Google that. Okay? To make the adaptive schemes robust to modeling and mismatch or whatever. Okay? That's very funny, okay, I'm going to tell you. There's another term is called adaptive robust control. Okay? Robust adaptive control, adaptive robust control. So, adaptive robust control makes better sense in the spirit here. You made a robust control, but you still want to learn the uncertainty so that I can have a sharper bond of the uncertainty. Then I can do better. That learning process with some adaptation or learning make adaptive control better and better. Robust control better and better. Okay? Or introduce some sort of self-optimizing mechanism to make robust control more and more optimal. Okay? So that is called adaptive robust control. Okay? And there are also a robust adaptive control to the adaptation schemes are more robust. Okay? So kind of very inspirational. Okay? So Oh, it's exactly 20 years ago, and Astrom. Did you see Astrom photo? Do you know this guy? Okay, let me show you a photo. You haven't seen Astrom's photo? I think it's last year, right? The photo with him. Have you seen this guy? On the left. That's Astrom, my role model. We met in a PID 2018 in Belgium. He's really good. And I also had some Skobet. Oh, this is Skobet. This guy is a Skobet. Okay, and Astrom. I have a picture of Astrom. This is his student Tom and Hogland. Okay, they wrote papers together. So you can see there are long, long slides, 84 pages. 84 pages. So we talk about feedback amplifiers. Very interesting. Do you know that in ideal amplifiers, so the open loop amplification is very high, like 10 to the power of 6. That high amplification gain. Then because of that, you introduce the feedback. Then you turn this point, if this is Earth, turn this point is called virtual Earth. Okay, virtual Earth. Okay, it's almost Earth. And then, because of that, you don't have current get into. So this is very nice amplifier. There's a lot of interesting things here. So important ideas is Bodhi's background, Bodhi's integral. We have talked about it. There's one thing we haven't talked is Bodhi's ideal loop transfer function. Okay, I'm going to show you now. Steady space, classical robust control, Bodhi's relation, delay margin, Bodhi's ideal loop transfer function, and did you see this? Fractional systems. Okay, so I'm going to go to the standard program here, feedback loop with GAN of 4, GAN of 6. Those are things we have learned. Oh, GAN of 4, he used GAN of 4. Nyquist stability. This point is called -1J0 point. So closed loop transfer function is used as T. T is also called complementary sensitivity function. And then we talked about conservative small game interpretation, sensitivity, S, sensitivity. We have seen this before, right? And this is Bodhi's integral, sensitivity, third. Then this is a right half plane zeros, apoptose. This complementary sensitivity function, they also have something related to zeros. Sensitivity. We have seen this before, right? And talk about water bed effect. Okay, you have seen this. Bodhi's relationship. What he did is to directly do the log to the transfer function G, then you have a real part and imaginary part. Real part is magnitude, imaginary part is phi. Okay. And he used to use normalized U, as a variable. So in the end, gain phase, the phase is linked to gain through this equation. So probably the phase is approximated like the gain slope on the body plot. Okay, the body plot. DD is the body plot. So, actually, I published papers on the Clegg integrator. Those bodies relationship can be broken. You can break it by using a nonlinear compensation. So this is only for LTI system. Delay margin, that's a separate topic. Smith predictor, I don't have time to go through this guy. It's amazing, interesting. Anyway. Now, okay. Here's something you probably never have heard. So basically that you have a body's plot originally was designed to be the repeater of amplifiers. So one cascaded with another one, but they discovered that if you cascaded several of them, then the whole thing will get unstable, because the signal will get delayed until you reverse the sign. Okay. So so basically they said for the loop, if you have a loop, and in the loop you have multiple amplifiers. So then you have add up with all the phase delays, okay, phase lags. If you lag more than 180 degrees, okay, and before you cross over, then you'll get unstable. So how, he said, how you can avoid that, that's what he said. When you do the gain crossover, okay, have a gain crossover, that corresponding crossover, while you cross over, you can cross over this way or this way with that slope. Okay? He said the slope, while you cross this one, if the slope is minus 20 dB per decade, it's like you have a function like that, okay? Something like that. So I think this should be one. I think it should be minus 1. But that was surprising. Okay? That's a negative sign. So you have omega GC divided by S. So basically, he said you have to have like 1.5, okay, minus 30 dB per decade when you cross it, and this is documented in Bodhi's book. Okay, 1947 book. Okay, so people didn't realize that this is nothing but a fractional integrator. If this is minus 0.15, okay. And so when people say Bodhi is ideal loop transfer function, you should be careful. It is actually a fractional order integrator. Okay, integrator. So if you have a system like this, okay, this system is a typical position servo system. So you have a velocity servo integration, you got a position, right? So velocity servo. He said, what if I design my loop transfer function is a C times P. L equals what? L equals controller times P, okay? C times P. If I put C times P is this one. This is called ideal. This is 1.5, remember? This is Bodhi's ideal transfer function. Okay? So that, what is your controller then? The controller will be a half differentiator and half integrator. Okay? So this is a fractional transfer function. And you implement that, you'll get this. So this is a fractional order control. So that's why you see in my course syllabus, I put fractional order control in it because this is intimately linked to robust control. Okay? And this actually talked by Astrom 20 years ago. And if you hear somebody say fractional order control is strange, show them this. Okay? Show them this. But you should implement this C, so then you have implementation, approximation of high order. We have better ideas than this, okay? So this is Auscalop's implementation idea. We have better ideas than that. And the implementation will be like this. So you can see this. So you can see this crossover is minus 30 dB per decade at gain crossover. What is this gain crossover? Is here is gain crossover. Okay, from 0 dB. Okay, 0 dB. So this is 0 dB to here. This is a gain crossover. At this gain crossover, I have minus 30 dB per decade. And then you can see the system decays. At this point, the phase is flat. Phase is flat, okay? And that means if you have something wrong in the system, your system has some gain is changing, then the whole body plot will go up and down, then omega gain crossover will go left and right. But when you go left and right, your phase margin is almost the constant. So in the large range, phase margin is constant. So that means your system is robust to variation in the gain. Okay, variation in the gain. Yeah, we got more stories about this for suspension. Okay. And that means no matter how many people sit in the vehicle, the suspension spring travels, maximum travel is always the same. Doesn't matter how many people there. Okay? This is called isodamping behavior. Isodamping behavior. Okay? And this is very good. So next 5 minutes. So the rest you can read this set of slides. Very interesting, okay? I feel very interesting. So I'm going to show you even more interesting thing. So it's our textbook. Problem 811. So 811, I think this is big enough for you to okay? Okay, the problem in 1970s and 80s, it was such a popular work. Say, for example, I give you A of S, that is an interval polynomial. So that is, you have a characteristic polynomial of a size of transfer function. And the polynomial coefficients are known intervals with known bounds. So all these A0 minus A plus, those are all known values, but you are in the interval. So you have an interval. This is called interval polynomial. Okay, interval polynomial. You have an order of n. Okay, you can ask n. Doesn't matter. So people believe that in robust control we end up with such kind of interval polynomials. And how to check the stability of this polynomial? How many polynomials we need to check? There are infinitely many. Okay. you can scan all of these. So if you have 10 of these, then in combination, you scan all of the interval and check out. It's not even possible. Okay, a combinatorial explosion. Okay. So Kharotonov is the first person to say, don't worry, you only need to check 4 of them. Okay, and the 4 of them, this is called Kharotonov polynomials. They construct 4 polynomials, only showing like the edges. So these are constant value, no longer intervals. Okay, these are uncertainties. Okay, no intervals. You said you only construct this K1 like this, K2 like this. So you use lower bound. The second one is lower bound. Plus, plus, minus, minus, plus, plus. There's a pattern. So this is also a pattern. Minus, plus, plus, minus, minus, plus, plus. So there's some. So if you think about this is as a cube, okay. So you have interval. You have another one interval. Is become 2 by 2, right? So it's kind of cube. You only check the 4 extreme cases. Okay, 4 extreme cases. Okay. So this is called edge theorem. So Kharotonov's is people say edge theorem. Edge theorem. So it's computable. Okay, computable. So if you check these 4 are stable, then you say this is stable. So they turn a computation hard problem to a simple problem. But the question is how you can check K1 stable or not. Okay, how can you check K2? You have something learned before. Do you still remember? Without, of course, you can solve giving all the coefficients, you can solve the roots, but without solving the roots, you heard about a theorem. It's called
the root array table.
Yeah. Routh-Hurwitz method. Okay, or Routh table. Okay, Routh table method. Okay, so you can check this one. Just use without using computer, you can do this job.
These are characteristic equations, right?
Characteristic equations. So this is very famous. Everybody treat this as the essence of robust control. I'm telling you, this is a joke. Right? If we look back, this is just such a small thing, and we can actually using a nominal model, like we do in the middle. So we go in the middle of the coefficient. We get a nominal model. Okay, we do a nominal model. Then we make sure that have a nominal model, put it divided by AS, divided by this, is a member of 1 plus WS and delta S. But WS is delta S is RH infinity. Okay, and make sure it's normalized to 1. Okay, then the rest is you find out the W. Okay, least conservative. How you can find out to make sure the original one is a member of this uncertainty set. Sorry, this is not a system yet. So this is A of S is uncertain polynomial divided by nominal polynomial, and so it's this part of the problem. So then we can check the stability of this one by this. This is the stability. So then you can use a small gain theorem to check the stability. Okay. So there are ways to solve this problem than original Kharotonov theorem. If you go to the literature, you will find thousands of papers on Kharotonov's theorem. Kharotonov is so famous in the 70s. People doing robust control treat this as a Bible. But today we see this is just a very small class of robust control. Therefore, when you do research, please pay attention to more general paradigm, just not the specific problem. So this is a very special problem. And people believe robust control in the end, they have to solve this problem, which is no longer true. Okay? Go to robust control toolbox in MATLAB. You need to start to do that. And read the menu, see what are the functions there, so you can already understand the new framework, new tools, so you don't have to reinvent the wheel. This is just for fun, okay? I'll provide the solution for you. I have that. With that, we can stop here today, and I'm going to have office hour after 3. So you come over 3 o'clock. I'll go until 5:30. Okay. All right. I'll see you around. Okay.